Okay, welcome back to part two. So we're continuing on with section 1.1, matter and energy. We're just going to break them up into little chunks that are a little bit easier to deal with. So this is part two. We'll continue where we left off. Up next is energy. Okay, um, the definition for energy has never been very satisfying to me, but it's what we have. It's the best that we have for now. Energy is the ability to do work. This is one of those points where words we use in everyday life and words we use in science may have slightly different meaning. Okay, so when we say energy, what we specifically mean is the ability to do work. We will define work then as the act of moving an object against an opposing force. Okay, anyway, we'll run with that for now. You have some idea in your head of what energy is, what work is. Let's try to add this to that idea. Okay. Now, there are lots of different types of energy. And this cool infographic from ThoughtCo just shows some different types of energy, right? There's mechanical energy, like gears. We have thermal energy for cooking, nuclear energy, chemical energy, electromagnetic energy, sonic, gravitational, kinetic, potential, ionization, and so on and so on. So these are all different ways of doing work, which is moving an object against an opposing force. But there are really two general forms of energy that all or others fit under. And so the first of those is kinetic energy. So two general forms of energy. One is kinetic energy. Kinetic energy is just the energy of motion, right? Just by the act of something having mass and moving, it contains energy. It can do work by its motion. So this could be macro scale, like a moving car. It could be atomic scale, like particles in motion, which we've already seen before, right? And we know that particles are always in motion, whether a gas particle are flying around uh, whatever space they contain, or solid state particles are vibrating in place. They're still in motion. Um, to think about those three states again, the particle motion can be ranked where gas state particles have more motion than liquid state particles, which have more motion than solid state particles, which means we can also say that the kinetic energy scales this way, right? So gas state has higher kinetic energy than liquid state, which is higher than solid state. And temperature can be defined as the measure of the average kinetic energy of the particles of matter. So we could say then that also temperature follows the same scale, right? Gas particles would be hotter than, or have a higher temperature than liquid state particles, which have a higher temperature than solid state particles, which should match your experience and your intuition, right? And so if you think about water, solid state would be ice, and the gas state would be steam. Steam has a higher temperature than ice, right? And it all has to do with the motion of the particles and the kinetic energy. Okay. Now, related to this topic is heat. I say related, it's different, and we'll get to the difference, but it's related as heat is the kinetic energy that is transferred from one substance to another, transferred from matter at higher temperature to matter at lower temperature. Heat always flows from hot to cold. And we can make some sense of this if we think again about particle motion, right? So higher temperature means the particles are moving more, we have more motion, and so they're going to be bouncing around more, and they can transfer energy upon collisions to slower moving molecules. The opposite would be like a slow moving particle and a fast moving particle bumping into each other, and the fast particle actually getting faster and the slow one getting slower, right? What's more likely is heat will, or the energy will transfer from the fast one to the slow one. Okay, think about billiard balls on a pool table in a similar way. So heat is transferred kinetic energy, and it always flows from hot to cold. Okay, let's go back to our two general forms. We said kinetic energy is the energy of motion, and the second is potential energy, which is stored energy. And this could be due to position or composition. So an example of positional potential energy is gravitational energy, right? Things fall from high to low. Another is compositional, could be chemical energy, right? You can burn a piece of wood and release energy, and what you're really doing is releasing chemical energy by breaking bonds within that substance. So the composition of what's there can store energy, or the position can store energy. So here's another picture of a ball in a mountain rolling down. Of course, we know that's the way it goes. It never rolls up. And so at the top is high potential energy due to its position. It's a very unstable position, right? It will fall if given the chance. And as it starts to roll, that potential energy is converted. As potential energy goes down due to position decreasing, kinetic energy is increased due to the motion. So there's always a trade-off, and you may have heard of the law of conservation of energy, that the total energy has to be consistent. So eventually it will slow down and have low potential energy, which is a stable position. Now, if this ball stops rolling and no longer has kinetic energy and it has low potential energy, what just happened to our conservation of energy? Well, these are two general forms of energy, but there are other places or ways that the energy can be dissipated or transferred. And there, as the ball rolls down, there would be noise and friction, which are both types of energy, and heat released. And so, right, eventually in the real world, eventually this ball will stop rolling. But the law of conservation of energy is still followed. Okay, so high potential, unstable, low potential, stable. Here's another example of composition. So think about the fuel in your vehicle or the fuel in your grill. It has high potential energy due to the chemical nature of that product. Now, when it's burned, the products that you get at the result are low in potential energy. And so the difference between the high potential energy of the fuel and the low potential energy of the product of the combustion is the heat energy that's released. In this case, it would be to cook your food. If it was a vehicle, the heat energy would be released in the form of moving a piston and moving your vehicle forward. Another example of potential energy in composition is food, right? The foods that you consume, carbohydrates, fats, have a high potential energy due to the chemical bonds inside. But when you eat it and your body metabolizes it into simpler products with low potential energy, the difference is energy released, used to power metabolism and move your body, and it's released as heat energy. So in this course, obviously this is a chemistry class, we're going to be looking at potential energy from a chemical change standpoint. So again, there are lots of ways that this can be broken down, but chemical potential energy is due to the composition of your substance. And here's another Thought Company infographic with some more examples. So all of these have to do with um, chemical composition changes and the associated potential energy changes of those. Okay, we will end this part 2 with this slide. Some words about words. As I said before, we may have slightly different definitions here in this class than what you think or what you're used to outside. Don't assume right away that you know what something means, but always be careful and precise in your language. If you mean to say kinetic energy, don't say heat. Be very careful about saying the right thing. Kinetic energy, temperature, heat are related, but they're not the same thing. So kinetic energy, fill in the blank, the energy a substance has as a result of what? Motion. The temperature is the blank of particles. Remember? What is this? Temperature is it's not the kinetic energy, it's the average kinetic energy of the particles. And heat is the amount of energy blank from one substance to another. The amount of energy transferred. All right, actually, I do have one more slide. I want to do one example to try to help uh, hash out these three definitions. So here, consider this. We have a large cauldron of water and a small pot of water. So consider these two and the amount of heat required to boil these two samples of water. And then think about the kinetic energy of these two boiling water and the temperature of these two boiling water. So I'm going to jump right in to start talking about this, but you can always pause it and think more about it. Okay, if we have two samples of water that are both boiling, let's start with the easier one. How do the temperatures compare? If they're both boiling, they're at the same temperature, right? 100 degrees Celsius or 212 degrees Fahrenheit. That's the boiling point of water. Doesn't matter how much water you have, it's always the same temperature. And why is that? Because temperature is the average kinetic energy. Okay? So you could say each molecule of water would have some average kinetic energy. So you could think that if you have more molecules of water, then you have a larger total kinetic energy. So even though they're at the same temperature, the cauldron has more kinetic energy. Now we're going in reverse order. Now think about heat that's required to make this boil. Well, we all know from experience that a small amount of water boils faster than a large amount. But why? Well, here we see, right? Because the large cauldron, you have to get more molecules up in kinetic energy, in motion, and heat is the transfer of kinetic energy. In this case, from the wood or from the burner up into the cooler water, so from the hot to cold. And so the amount of heat required to boil these two samples, the cauldron would require more heat because the total kinetic energy is higher, even though the average kinetic energy is the same. Okay, we will end part 2, and we'll do one more part to finish up today.